This segment discusses some of the design issues in developing a hula hoop. And I'm just going to first of all point out some of the components that are visible here. Starting at the top, we have the crown piece, which prevents the hoop from flying off the top. Then we have, of course, the pole, which actually does not rotate. It revolves, but it doesn't rotate. And then we have the launch pad, which is actually a conical platter. And below that you can see there's a encoder skirt here with 50 slots in it. And then of course there's an optical coupler, which is detecting these slots and bars in the encoding ring. I don't know if you can see there, but there's a piece of a red straw slipped over one side of the optical coupler because the video lights that I'm using here are so bright they saturate the receptor for the light sensor. But when I don't have big lights on, I can take that little sleeve off and it works fine. So below that, of course, we have the motor mount chassis, which, if you can see inside here, we have a flexible coupler which connects the output shaft of the gear motor to the main axle. And so this fits on the main axle as well as on the motor shaft. And of course we have a housing below that, and the motor is in the back. So the gear motor looks like this with an output shaft off center. And of course that's a smaller shaft than the axle. So we need it fits the other side of this coupler. So this is a flexible coupler to mate these two dissimilar shaft sizes without and keep them coaxial. Now we also have, of course, a stand that holds up the optical coupler, and in front here we have a little computer with a LCD display that shows the speed based on this optical coupler here, and it shows the height, which is based on this sharp optical sensor here. So this is a optical distance sensor. These things are kind of weird. They actually have two lenses. One emits light and the other one receives light. And the receiver side has two sensors in it, so the light goes up to the object and bounces back down into the receiver. And the further away it is dictates that there's a slightly different angle coming back, and the two sensors that are in there decide what the angle is based on how much of the light hits each sensor. So it's not very good for this application because as the hoop crosses this beam, it's interfering with the ratio of light. You know, you're cutting half the beam, so it's interfering with the ratio of light that hits those two sensors. So it's all over the map when the edge is actually just entering or leaving the beam. And so we can sort of do something with the data, ignoring the leading and trailing edges, but it's quite problematic. I really just wanted to see exactly how much problem this thing had when edges were crossing the beam. I knew it was going to be a problem, and it is. So I've got a little bit of software in there to deal with it, but it's not that effective, and it would take quite a bit of work to make a really good routine to get rid of the erroneous readings from the edges. So those are the main components. And next I'll talk about each one and the problems associated with designing them. Now, in the previous section, we described the secret sauce or scientific principles that allow the hula hoop to work. But that's light years away from figuring out all the design parameters to make a working system. So how do we decide like the diameter of the pole or the hoop or the cross-sectional shape of the hoop or the pole offset from the middle of the platter or the angle of the cone on the platter or the speed of rotation or the amount of power it will take to run, or how to balance this offset pole because it's going to create a kind of a wobble. Or you know how to stop the hoop from flying off the top. So we also need to know how strong all the components need to be. And we have to also figure out how to make the whole system rotate without rotating the pole. So we have to have the pole revolve without actually rotating. And of course there's a bunch of other details like gear ratios and bearings, and of course to figure out what electronics are needed. Now, since I know all the principles involved, I could probably calculate all these parameters and eventually come up with a working design. But that's not exactly what I did. I mean, I simply visualized the entire mechanism and every component in the system in full 3D animation, and I visualized what each component had to be to make a working system. So, you know, when people talk about a brain as being the best computer, it's just a matter of letting it out for a walk once in a while. Anyway, then I just purchased the necessary components that I didn't have and designed the rest in CAD to be 3D printed. And it all worked. Well, actually not exactly. I ordered a bunch of gears and bearings, but of course they were affected by some viruses going around. Whoa, we have a visitor hogging the limelight. So the three of the companies that I ordered parts from canceled the orders after I ordered them, and that left me with no gears, no bearings. So I decided I would have to actually 3D print these things, and of course that's all fine, except that, you know, gears are going to wear out quickly if they're plastic instead of metal. So I decided that I would need to use proper involute gears. So I was going to design these involute spur gears. So I researched that, and you know, I came to the conclusion like the spur gear design is such that the teeth are actually curved, and when they are rotating on each other, they actually just they roll. Each tooth rolls on the other tooth, so there's no real slipping and sliding friction in there, and that lets the gears last a lot longer. So I figured for plastic gears, that's what I was going to need. And of course I researched it a bit more, and I came to the conclusion that whoever designed the whole concept of involute gears was one smart cookie. So I figured I better chase that down, and so it turns out the first analysis I could find was done by one of the most amazing intellects of all time, Leonhard Euler. You know, you've heard of great minds like Einstein and Newton and Maxwell, but then you have minds like Beethoven and Hawking, and especially Euler, who accomplished spectacular intellectual feats despite having incredible handicaps. You know, if you think visualizing this machine was a neat trick, you should explore what Euler could do, and did do, even after he went blind. Anyway, back to gears. my CAD system can't do gears, and it would take a lot of time to actually calculate and figure out a way to draw these involute shapes. So I found FreeCAD, which actually has a built-in function to do involute gears, and that's the way to go. If you need involute gears, FreeCAD can do them with just a couple of strokes of your mouse. Very, very cool. And I'm not going to switch to FreeCAD because it has some other things that I don't like as much as my CAD system, but for doing gears, it's great. Anyway, the things you got to do when you got a virus to contend with. So in this device, there's a gear on top of the chassis which is frozen to the chassis and it doesn't rotate. And then we have a gear that's connected to the pole, which of course does rotate with respect to the platter. But if this was the gear connected to the pole, if I rotate it, you can see that the shaft is rotating. So what we need is a third gear, an idler gear that goes between these two gears. It's identical, but it reverses the rotation of this one, so that it's actually not rotating as it goes around. So just the idler gear is spinning, and it's spinning twice as fast as this thing rotates, which is another difficult concept in gears. But ultimately, this gear goes around without rotating, and that one's not rotating, but the idler gear is rotating, and it's causing this guy to actually not rotate, just revolve. So it's pretty complicated, but another interesting fact, of course, is that if you rotate this guy around the other one, they're identical gears, but this one actually rotates twice in the time that it goes around this one, and that's not intuitive to me, even though I know why it happens. You would think that these gears are completely interlocked, one to one, and that you would get the same number of teeth as you go around, so that it would just rotate once, but it actually rotates twice. And if you can get that concept, you should pursue a career in mechanical engineering. So that's gears, and it's a little bit complicated, but that's one of the secrets to this whole mechanism, is that it can make that pole rotate without, or revolve without rotating. And if you think about it, that's the way you would use your finger too. Your finger doesn't rotate when you're spinning something on it. Your finger is just wobbling in a circle, just like this thing. But your finger, of course, can't rotate every time that the hoop goes around. So that's the action we want on the spinning pole. Now, of course, there's going to be some stresses on all the axles and so on in this design, because this pole is trying to torque over to the side, and so I wanted to have bearings. That's why this is so tall. I wanted to have a bearing down below and one above on the main axle, so that it couldn't rotate or couldn't bend over. But of course the bearings didn't come in, so I figured, well, I'll make bearings that look just like them, out of plastic. And this is what that pillow block looks like, out of plastic. So now it's just a bushing, so that the shaft can go through that bushing, and it can't, like, it's quite tight. It's just got enough slop so that it rotates freely, but it's not going to tilt. So of course I made a bunch of these things. There's two for the main axle here, and then there's two to keep the pole on the platform or the platter from tipping as well. So there's some depth here which has 2 bearings in it. Well, of course now they're just bushings. And of course one of the bearings finally came in. So that's what the actual bearing looks like. It's too little too late, but it's there now. But the gears didn't come in. So let's talk a bit about the pole. The pole is made up in sections that kind of look like this. There's a smaller section here that can fit into this section of the next. So it's made up of different sections, and they just fit together like this, very tight. But that allows me to make it any height, and I kept it fairly short so that we could fit it in a video. It's even tough with the height that it's at, but it's perfectly adequate for demonstrating the concept. So inside here we have an Arduino Pro Micro with a Nokia display, a 5110 LCD. I didn't use these sockets there. I just soldered them directly to the card, and I didn't put this Bluetooth module in there. But it's basically the same as this module. And the case for this is designed so that the electronics slide in, and there's a little hole here to have a button that allows me to push the reset button. I don't know if you can see that, but it's just reset. And that's necessary for this particular Pro Micro because that reset button is the only way to get back into programming mode. And there's a little shaft in here which holds the backing plate on, and that shaft is exactly behind this point in the display where there's an elastomeric connector that tends to bow this card, and then the elastomeric connector gets a little flaky, a little intermittent. So the card that's on the display is quite thin, and that elastomeric connector eventually bends it down a bit. So that shaft is right there, providing extra support so that the display doesn't go flaky on me. That's quite a common problem with these displays. So lots of little details go into the design, a design like this. But and it takes a little bit of work to get it all together, but it's pretty cool when you can actually visualize something and then just build it, and it does what you visualized. There are a couple of notes. You know, when this thing is going, this is not much of a slope on the edge here, and it's really not providing a lot of tilting force, so it has to be going reasonably quick to give us an upward angle, and it will take a while to get up there if we don't have a good angle. But I did manage to get the friction to be extremely high on the pole. So you can see here I'm not pulling on this hoop at all, and it's really almost stuck to the pole over there. So that stuff is very sticky. It's a kind of a silicone tape. But if I had a better angle on the hoop, I could run this at a lot slower speed, and it would sort of hang down at this angle, but still it still would rotate up. That would be kind of cool to do, but I would have to design a hoop with better aerodynamics, because this has to be going fairly fast in order to create a tilt. So there's all kinds of little pieces that I designed in between, because when I was going to these gears, I was worried about the gears breaking, so I made these big gears. In the end, I decided I could get away with smaller gears, but you know, this thing was going to adapt these bearings to allow the bearings to attach to the gear, and then the gear would be jammed in there. And lots of stuff that you do when you have to revisualize the whole process. You know, I had planned it all with these metal gears and had to rethink it a couple of times as I decided that I was going to actually do some 3D printing instead. But now I have a nice platform. This piece of wood is just a cutting board from the dollar store, but they just make great bases, very cheap and nicely finished. But now, so I have a nice demonstration project where I can show the principles of how you can make a hula hoop go up a pole. It's not the same as when you're using a hula hoop on your body. This kind of hula hoop needs all kinds of different things. You can't flip it up with your hip. You just need to figure out a way to generate some vertical force. There are other methods, but if you want to try them, be prepared for lots of experimentation. The other methods are even more difficult to make happen.